Hey, welcome back, Marauders. This is section 3.5 Kinetic Molecular Theory. It's my favorite section, so let's get started. The kinetic molecular theory explains why the equation PV is equal to nRT works. So it's kind of the theory behind all those mathematical equations that we've been using. We know how to do the calculations, but we should also be able to explain why they work and how they work. So there's 5 parts to the kinetic molecular theory, 5 assumptions that we make. And the first one is that the particles are in constant motion and that their collisions cause pressure. So we've seen in our simulations, the gas particles are constantly moving, they're constantly bouncing off of each other in a random way, and they're also bouncing off the sides of the container. And that's what we measure as pressure, is all those collisions that the particles have with the sides of the container. And if they're colliding more frequently or with more force, then we have more pressure. The second part is that the particles are so small we can ignore their volume. So in the equation PV is equal to nRT, the volume is not so much the volume of the molecules, but it's really the volume of the space in between them. Gases are unlike liquids and solids in that there's a lot of space between the particles. So the size of the molecule is not really that important. What's important is how much space is between them, and we just measure that as the total volume of the container. The third part is that the particles do not attract or repel each other. So we know that like in solids and liquids, the intermolecular forces, they attract the particles to each other. And we assume that in an ideal gas, the gas particles do not attract or repel each other at all. We'll find out later that with real gases, that's not entirely true, but it's a pretty good assumption for most gases that they don't really attract each other. They move independently of the other particles. Part number 4, energy is transferred during collisions, but average kinetic energy is constant at a constant temperature. So the particles are constantly colliding, and those collisions are perfectly elastic. All the kinetic energy is conserved. One particle might start moving a little slower, but it'll give all of its kinetic energy to another. So some are moving fast, some are moving slow, but the total amount of kinetic energy remains the same even after the collisions that occur. And then part 5 is that the average kinetic energy is proportional to the Kelvin temperature. So when we measure temperature, we're really measuring the average kinetic energy. And as you increase the temperature, the particles move around faster. This graph right here shows the particles moving around faster at higher temperatures. So this graph right here is called Maxwell-Boltzmann distribution. And it shows that not all the particles are moving exactly the same speed. Here we have one at 100 degrees, and you see that's the distribution of how many particles are moving at each speed. So some are moving really slow, some are moving really fast, and then there's kind of an average here in the middle. And then we see that when we heat it, so if we go from 100 to 300, the curve kind of gets shifted to the right and stretched out. The total area under the curve is still the same because we have the same number of particles, but now some of those particles are moving faster. There's still some that are moving slow. There's some that are moving much faster, and the average has increased when you went from 100 to 300 degrees Kelvin. And then same thing when we go to 600 and 1,000. The curve keeps getting stretched out here to the right because more of the particles are moving faster, and the average velocity of the particles is faster as well. So what you're measuring when you measure temperature is really how fast the particles are moving. As you increase the temperature, so here's the low temperature over here on the left, and then the higher temperature over here on the right, you're going to have more particles that are able to turn to vapor. So if this was a liquid and you have a higher temperature, then more of the particles to the right of this E right here, that's the minimum energy for them to escape and turn to a gas. You have more particles that are able to escape and turn to a gas, and therefore you have a higher vapor pressure. This graph right here shows how vapor pressure varies with temperature. And so since at a higher temperature, more of the particles are moving faster and have the energy required to escape, then you get a higher vapor pressure as you increase the temperature. And the vapor pressure, when the vapor pressure is equal to 1 atm, when it's equal to atmospheric pressure, then that's your boiling point. So this graph right here is for water, and we know that water boils at 100 degrees Celsius. That's because the vapor pressure of the water is equal to atmospheric pressure. So it's not just turning to vapor on the surface, but it's turning to vapor throughout, and that's why boiling water starts to bubble, not just on the surface, but throughout the whole solution. Here's a picture of the Maxwell-Boltzmann distribution again, and this one's showing something slightly different. Instead of showing different temperatures, we're showing all the same temperature, but we're showing different gases. And so all gases have the same amount of kinetic energy at the same temperature. So at this temperature, all these gases have the same amount of kinetic energy, but they achieve that kinetic energy in different ways. The heavier gases, so the xenon, can move pretty slow. Since kinetic energy is made up of mass and velocity, they can have a slower velocity, and they make up for it with their higher mass. So they still have the same amount of kinetic energy, but they do that with a lot of mass and kind of a slow velocity. This curve over here to the right is helium, and so that's the lightest of these gases. And since it has such a small mass, it needs to have a really high velocity to make up for its lack of mass and to keep that same total amount of kinetic energy at that same temperature. So to summarize this graph, at the same temperature, lighter gases are going to be moving faster, and heavier gases are going to be moving slower. We can notice the speed at which gases are moving if we measure their rate of effusion. Effusion is how fast gases can escape through a really tiny hole. So like in a balloon, the gases can escape through the balloon because there's really tiny holes in these balloons, and the particles can just randomly be bouncing around and hit one of those holes and be able to escape. And so helium, since helium has a really small molar mass, it's going to be moving really rapidly, and so it's going to effuse more quickly than a gas that's heavier like nitrogen. Nitrogen, the particles are going to be moving slower, so it's going to effuse more slowly. It's not really because the particles are smaller and can squeeze through a smaller hole. The reason is that they're moving faster, and so they have more random encounters with that hole that they can squeeze through. And so you may have noticed something like this. If you have a helium balloon and then just one filled with nitrogen and oxygen, like one that's just filled with atmospheric gases, the one that's filled with helium will deflate much faster. So here's the first day, and then here's day 2. The helium balloon has gotten much smaller because the helium particles are moving faster. They have a higher average velocity, and so they're escaping this balloon more quickly than the nitrogen. The nitrogen balloon stays filled a little bit longer because the particles are moving slower, so it takes them a little bit longer to just randomly find those holes and effuse out of the balloon. That's it for this section.